So my name is Datta. I'm an assistant professor of digital twins. This is at TU Delft. And yes, today I'm going to be talking about geopolitics and the digital twins workflow. I work on polar regions, and that's especially the Antarctic ice sheet, focusing on things like extreme snowfall, surface melt, and superglacial lakes. You can find me here. This is my website. And what I'm showing in the background here is an image of the Larsen Sea ice shelf, which I focus on. And, I'm obviously not going to be talking about the specific science here, but more importantly, how this affects the way we do science. So just in a general way, most of the things that I work on is relating ice sheet mass to sea level rise, and especially over Antarctica. So this is very idealized, but what I really want to emphasize is the scale of the data that we use and how messy that can be. And so what that means is that I mostly work with climate models, which are at a quarter degree resolution, 1 degree resolution, and that's both models that are produced by, for example, the CMIP6 catalog, but also models that I run myself to do experiments. And additionally, I've worked with a lot of satellite data, which is on the scale of meters to kilometers. But finally, something that's fairly important to us is also observational data, which is at single points. And this echoes a lot of concerns, I think, within other communities, but it's really important to understand how necessary that data is, but also how it's actually collected and kept. So, for example, a campaign that is in a specific area, this is something that's collected by people who don't tend to be very savvy about how that data is actually kept. And that's kind of important because within Antarctica, for example, you need data at all of these scales. It's not just the climate model or the ice sheet model. It's also the satellite data, but it's also often CSV files that someone has created based on data that they collected on the ground. And so just as an example, this is a campaign that I was a part of. It's NASA Operation Icebridge, and it's an airborne campaign. So this is the kind of things we look at. But the data from airborne missions is on the scale of, say, 30 centimeters. That's compared with data that's on the ground, which is, point scale compared to satellite data, compared to climate model data. So all of these things kind of work together. The other thing that's kind of special about Antarctica, and this, gets back to the geopolitics, is that we work with a lot of different countries. There's data coming in from a lot of different countries, and we use all of that coming together to make an assessment of Antarctica, because nobody owns Antarctica, and at least so far the treaties mean that we have scientific basis, but it's not mined for any other purposes. So that kind of coordination is especially true when it comes to Antarctic science. So just as another example of the kind of data that I look at in particular, this is from Planet SkySat. And as a postdoc, I was lucky enough to be able to work with this commercial company and task a satellite, a very high resolution satellite, over the Greenland ice sheet for an entire summer. And this was a massive amount of data that was collected as a part of this experimental program called the Small Satellite Data Buy Program. The thing about this is, though, it was contained inside of the U.S. From my perspective, I didn't even think about the way that the data was protected, or whether it was U.S. or anything else, because I tended to work with people who were from the Netherlands, from France, from everywhere in the world. Is that as far as I knew, all data was public. And I mean, maybe this is something else to emphasize, is that as a user, and I had a previous career as a software engineer, scientists are, if everything's working well, we're remarkably ignorant about what happens behind the scenes. And so from my perspective, I collected all this data, this massive amount of data, and it should have been used for everybody. It should have been available to everybody. And in fact, even then, that was not the case. And obviously, that's gotten a lot harder now. Just to go on about this project in particular, this used data sources from multiple satellites. So I used ISAT-2, which had just launched at that point, imagery from SkySat, as I mentioned, but also Operation Icebridge, which is an airborne mission from NASA and controlled by the United States. But the satellite data sources that I used are from different agencies, different countries. So I'm pointing this out specifically. The science of this was to collect data volumes of superglacial lakes. But, getting away from that, this used Planet SkySat, again, commercial, Planet Dove-R, commercial, Sentinel-2, which is European, and then Landsat, which is American. Again, from my perspective, I was fairly ignorant about where any of this data came from. I downloaded, or I had it available on a common HPC facility, and didn't think about it much more than that. But however, this data, while that initial project and then that paper concluded, that was used for another project. This was IHARP, and this is an institute in the United States that I was a part of that's harnessing the data revolution for cryospheric sciences. And that data was used as a training data set where K through 12 students from all over the world have to help to define features on this imagery. And that was used for machine learning algorithms for a SIG Spatial 2023 Cup. And so just to sort of emphasize, this is something that was technically, data that was started out being private, ended up being extended for U.S. users, but was ultimately used very publicly. And I'm not entirely sure that this would be possible under the current administration. The other major thing that I tend to work on is, or most of my work is Earth systems models. And so we've talked a little bit about CMIP6 and the importance there. I'll go into that more detail. But I want to kind of break this down because typically from users, for example, from the commercial or risk sector, they use CMIP6 data outputs, but all of these are internally require a lot of data to calibrate, to run experiments, to perfect. Within the cryosphere in particular, I'm just pointing to the bottom right here, melt channels and ice shelves, that uses data from things like, especially for parameterizations, it uses data from various campaigns, ice sheets and glaciers for initialization. The snowpack, definitely. Snowpack is something that we use a lot of data that comes from field campaigns. And so, you have an Earth systems model. The coupling between each of these elements is something that is very, requires a lot of software expertise. But the science of it, the physics of it, is something that requires a lot of data as well. So we want to touch a little bit on CMIP6 and so, for those who don't know, this is the most current climate models who are data available, and this is from multiple groups. And most of this is used for the IPCC assessment reports and is also used for various commercial outfits as well as science goals. But the main thing is these are different models that are housed in different places, which are compared through a very rigorous process involving people across the world. So this means this has a lot of implications for people not being able to collaborate. So from my perspective, one of the things that's fairly important is the continued availability of CMIP6 data. And currently that doesn't seem to be a problem, but that could become an issue in the near future. But the other thing I want to point out is the way that the data is changing right now, and this has to do a little bit with my role within digital twins, is that, I mentioned that the climate models are at 1 degree resolutions, but in fact, I work with a variable resolution ECM, so the scales of these models and the data volumes of these models is growing enormous. So for someone like me producing a climate model experiment, that's turning into a very, very, very heavy amount of data. So copying that over, most recently, just because I was afraid of the situation in the US, I ended up copying over a lot of my data, and I didn't even think about how massive it was. But one of the major problems, and I'm going to move on here to many of the ways that it is analyzed, just because it might be relevant to the workflows here, is that in addition to the data itself, and the production of the models, there's a lot of processes that go into the analysis, which for me, I use quite a bit of AI. So this is actually pretty relevant to me as well. So finally, I'm just going to pick up on the main things that I do here is that, that involves running climate models, using model outputs for analysis, especially the CMIP6 catalog. There's also the collection and processing of data. And by that, I don't mean internal to an HPC. I mean actually collecting it on the ground, being able to share it globally, and being able to process it in a format where it's able to be co-registered between things like airborne campaigns versus ground campaigns versus climate models. And a lot of the problems here is that we have very large data volumes, which are difficult to keep in parallel. There are different scales, and there's a lot of interdependencies that aren't very clear. And a lot of it has to do with the way that we as scientists work, which means, I'll flip over here. So for modeling in particular, for example, we run a model. This is typically on high performance computing centers. And for me, where I work, it's currently centralized in the US. But in terms of the way that the model is changed, that's something that internally we do things like, we have data that's sitting on our computer. We have data that's sitting in some repository that isn't interconnected with other repositories. So often it's very unclear. And again, the major problem with this is that there are massive outputs, especially with CMIP6 data. And finally, that kind of analysis process is often that we have code bases which aren't very clean and often difficult to reproduce, which is another problem with the science. So the risk in terms of a geopolitics is the availability of input data and storage. So the input data, the problem here isn't strictly about specific data that is currently being collected on the ground as much as to even start up and run the model. So currently, when I have done model runs most recently, this has been in Colorado. That may not be available in the future, so have to move all those resources somewhere else. And running that model is not easy because a place like NCAR is somewhere which houses not just scientists, but a lot of software engineers, and all of that expertise is housed very locally. So one of the problems that I see here is that you have models that are used globally where the outputs are very necessary for purposes across the globe, and yet ultimately they're actually run only in one location, and therefore very, very vulnerable to any sort of geopolitical context, which may cut off the use of those resources or make the data unavailable. So I'm emphasizing the running of the models itself, being able to run the models in different places, being able to say if something is open source, if the model itself is open source, it's not simply that the code is available, but that you actually have the infrastructure to be able to support runs, to be able to run it if the US, for example, goes down. Or especially in the case of the US right now, as the National Science Foundation is being underfunded, and that might actually take away the resources for the High Performance Computing Center. Or that's a risk. I don't know that that's true, but we'll find out in a few months. For observational research, which I conduct as well, some of this is a tasking and retrieving of satellite data. The project that I mentioned before, where I was able to task a satellite with Planet, I ended up working very closely with engineers there. And what was fairly clear to me is this is a very complex process that requires a lot of trust. Even between a governmental agency, and for me, I was within NASA Goddard, and a private company, that was actually fairly difficult. There were certain things they wanted to keep private. There was plenty of data that I had no access to. That was difficult. If I scale that up to working between countries that don't trust each other, I can see that becoming very difficult. And finally, so the availability of data and the continuing collection of data. So one thing I want to point out is that within the US, a lot of data is used for reanalysis in, for example, for ECMWF. So because of that sharing has been, especially from NOAA, has been constant in the past, we haven't really had to think about it. And now all of a sudden, a lot of the question is to produce the reanalysis that is really critical to a lot of climate science. Is that data going to be available in the future? So I'm going to talk a little bit about, and just generalizing about the current geopolitical landscape. One of the major things, and this is just going to be without identifying information, talking about the experience of some of my colleagues in the US, is a lot of uncertainty about what's happening. So data resources aren't necessarily being cut off yet, but in many cases, we're actually fairly frightened that this will, hold on, I'm just going to admit this person. If data resources aren't available, they actually don't know where they're going to be cut off, because the administration had actually come in and demanded access to servers in the past in certain cases. So that's something people are afraid of. So even if it hasn't happened yet, it might in the future. And so controlling for that. But I think that more importantly, it's that we've actually become, and I say this as a scientist, has become a little bit clear about exactly what is supporting us. The large-scale infrastructure, high-performing computing centers that we depend on, we haven't thought very much about exactly how that works, how a lot of the data is shared. If everything works well, we can stay ignorant. Well, we can't stay ignorant anymore. So I'm very glad to be here, starting to think about these questions. So again, the main challenges are are having software being able to actually be run in multiple locations and aggregating the data. So, a lot of efforts in digital twins is to have data lakes where a lot of the data that is relevant to any one specific subject is available in an easily accessible format. But there are some opportunities here, and that's the possibility for replicating a lot of these computing environments so that we truly are global. Because I would say, to emphasize again, this is very true for Antarctic science. We operate globally. The science is global. There aren't really very many boundaries here in terms of how, we're all affected by sea level rise. We tend to work together, and when it comes to the continent, and we should be able to replicate things like climate models, if that's the case. So with that, thank you very much for your time.